An operating system acts as the essential bridge between the user and the computer hardware. It manages all the complex resources behind the scenes. Think of the operating system as a restaurant manager. The manager directs the waiters, who represent your applications, and the kitchen staff, which represents the hardware, to ensure customers are served efficiently. The operating system effectively manages memory, storage, and CPU usage. It provides a friendly interface for users and coordinates all communication with hardware. To keep your computer stable, operating systems use a concept called dual mode operation. Think of it as a bouncer system for your hardware. In user mode, your apps run in a restricted area. They can't access hardware directly, which keeps a simple app crash from destroying your entire system. In kernel mode, the system core has full, absolute control. It performs sensitive operations that the user-level apps aren't allowed to touch. When an app tries to access hardware directly, the mode switch mechanism intervenes. The kernel checks if it's allowed, protecting your system core. Remember, user mode keeps things safe, while kernel mode does the heavy lifting. This separation ensures that one bad app doesn't sink the ship. Operating systems come in different styles to handle tasks efficiently. First is the multi-programmed operating system. In this design, the memory holds several programs at once, so the CPU is never idle while waiting for I/O operations. Next, we have time-sharing systems. Here, the CPU switches between tasks so rapidly that users feel they have the computer to themselves, even while many are using it simultaneously. Finally, there are real-time systems. These are designed for critical tasks that must finish within a strict deadline, such as medical devices or car braking systems. Efficiency is measured by response time, not throughput. Remember, multi-program systems maximize CPU use, time sharing focuses on user interaction, and real-time systems focus on absolute reliability. Think of a process as a program that is currently running. It's an active entity, not just code sitting on your hard drive. The operating system tracks every process using a process control block, or PCB. Think of this as the digital ID card for a task. It stores everything the OS needs to know, like the process ID, its current status, and where it left off in memory. Schedulers act like traffic controllers. They decide which process moves into the CPU. Processes cycle through states. They are ready to work, running on the CPU, or waiting for input like a mouse click or file access. And that's the core of process management, keeping track of every task's ID card and carefully directing traffic to keep your computer running smoothly. In Linux, everything is organized within a single hierarchical tree, starting at the root directory, represented by a simple /. This structure keeps all system files and user data in a predictable, organized path. Programs often need to talk to each other. Linux uses pipes, which let the output of one program flow directly into the input of another. It is a powerful way to chain small, simple tools into a complex task. Ultimately, the operating system acts as a silent orchestrator, managing files and communication to keep your digital world running smoothly. Understanding these basics helps us appreciate how our devices function every day.